In this video, we're going to talk about fluids. Fluids have a really low density. There aren't a lot of particles per unit volume. The things that we consider fluids are liquids and gases, and all of these things move to fill the shape of their container, so we call these fluids. So I know most of you are thinking of a liquid as a fluid, but a gas is also considered a fluid, so just keep that in mind. To calculate pressure, we just do pressure is force divided by area. And then we have a couple of units that we use for pressure. The Pascal is a force of 1 Newton per meter squared. And again, that's just going to be a force divided by an area. And meters squared is an area, so that's where they're getting that unit. And they call that the Pascal. Okay, and then we have the atmosphere. This is used really often. I used it a lot when I was scuba diving. We would calculate the atmospheric pressure at different depths. And this again is a unit of pressure. And it increases every 34 feet in air or fresh water. So if you go down 34 feet, you're at 1 atmosphere, and two sets of 34, which would be 68, you're at 2 atmospheres. And salt water is a little more dense because it's got all those ions and stuff in it. And so it's every 33 feet for salt water. And then a barometer is something that we use to measure air pressure. You can see if it's lower or higher. A lot of times if there's going to be a storm coming, they'll say they've detected a low pressure area, and that's usually a storm. Now, okay, so we've got this formula or this problem, and we need to figure it out. So let's see what we know. We have a child, and he weighs 364 newtons. This is a force due to gravity. And he sits on a 3-legged stool which weighs 41 newtons. So that's also a force due to gravity. Okay, but that's the force due to gravity of the stool, and this is the force due to gravity of the child. And then it says the bottom of the stool's legs touch the ground over a total area, it should be gone, over a total area of 19.3 centimeters squared. And this is an area. And then it says, what is the average pressure on the child that the child and the stool exert on the ground? And so our pressure formula is pressure is equal to force divided by area. Okay, and we have a couple forces, and we have the child, and then we have the stool. And since the child is sitting on the stool and they want the force that the child and the stool create, we need to add these two together. So we can just add them together, and we'll get our net force, which is the one that we're really going to worry about. And it's going to be 405 newtons. Okay, and then they gave us an area, and it was in 19.3 centimeters cubed. Now, because they didn't say they want the pressure in pascals, we can just leave it like this, and we'll just call it newtons per centimeter squared, and that way we won't have to do any conversions. So we'll take our pressure is equal to our force, and our force is that 405 total newtons. And then we're going to divide it by our area, which is 19.3 centimeters squared, and we're going to get 20.8, 20.98 actually, newtons per centimeter squared. You can't call this pascals because these are in centimeters and they need to be in meters in order to use pascals. So just kind of keep that in mind, that we're just going to have 20.98. Okay, so now we have another question. We want to know, how does the pressure change when the child leans over so that only 2 legs of the stool touch the floor? Okay, so we're going to use that same force that we had before, because we still have the kid and we still have the stool. And then our total area was when all 3 legs, that was 19.3 centimeters squared. That was when all 3 legs were touching the ground. And now we only have 2 out of the 3. So we can multiply this by 2/3, and this will give you the area for just 2 of the legs instead of 1, or instead of 3. Okay, now you can do the same thing. You've got your formula. Pressure is equal to force divided by area, and you can take your force of 405 newtons, and this time you're going to divide it by 12.87 instead of that 19.3. Look what I did, 12.93. Very good. I don't know if I can erase the whole thing, so we'll just do this. And it's 12.87. And so we'll have 31.47. Again, it's newtons per centimeter because we did not change it into meters here, so we cannot call this a Pascal. Okay, it has to be newtons per centimeter squared. If you want it to be a Pascal, you've got to convert those centimeters to meters. Okay, so now we want to talk about how some of these liquids behave. Viscosity, I really like viscosity. It's a really fun word. And it's resistance to flow. So like this could be like some sort of gel, and this, I don't know, this looks like maybe like, it could be like something you put in your hair, and then we could have syrup here and honey, and then this could be water. And so the thicker the liquid is, the more resistance to flow it has and the less viscosity it has. When we talked about Reynolds numbers and we talked about the critters that live in under the microscope, those critters, remember the water seems more viscous to them, like tar. Remember, if we were going to swim through water, it would be like tar. So that's viscosity. For some reason, I think that is a really fun word. And then surface tension. This is the inward pull by the particles in the interior. So you can see here, we have a meniscus right here. And remember, when you guys are measuring stuff in the lab, this would be where you measure. You wouldn't measure at the top because this actually is not water. This is just a kind of like a bowled-in shape, almost like the shape of a contact. And that's not actually water right there. That's the meniscus. Sometimes you guys might notice if you fill up a glass of water and you fill it up really, really, really high, you get that little bit of water that's coming up right there. That's also a meniscus. And that surface tension is pulling that together. You can do a lab where you see how many water droplets will fit on a penny, and you'll get this little thing like this, and that's the adhesion and the surface tension of those molecules. Maybe you did that in biology. Adhesive forces, these are attractive forces that act between particles of different substances. I don't know if you guys have ever done this. If you put a paper towel near a liquid, it'll actually suck it up, and you can see it kind of pulling it up. This is a really fun one too. You can take celery or a flower if you have like a white carnation, and you can put it in dye, and it'll actually suck it up, and it'll turn the leaves red or whatever color your dye is, like blue. And then this is a really fun one. This is a calendar that I saw, and so this would be like October, and October would be this color. And they have the way the liquid is and the way this material is it fills up for like each day, and so you can actually like this would be like the 10th or whatever of October, and so you can get an idea of it's kind of a neat little like monthly calendar. Pascal's Principle, this is pretty key. This will be one of those vocab words that you want to memorize. You might see it on a quiz or a matching section of your test or something like that. And it says that any change in pressure applied at any point on a confined fluid is transmitted undiminished throughout the fluid. So I'm one of those squeeze from the middle toothpaste people. My husband's at the end. He likes to squeeze the end and squeeze it real nicely. And even though I'm type A and everywhere else in my life, I actually squeeze the toothpaste from the middle. And because of Pascal's Principle, I still get toothpaste. Just the way, even though my husband does it the right way, I squeeze from the middle. I'm still getting toothpaste. You can see over here, they're actually, it squeezes the toothpaste up in here, and then it actually is a nice little thing, and it squeezes it real nicely, and you have this little thing for toothpaste. We just use this, but it's all because of Pascal's Principle. And then the last thing I want to talk to you guys about today is this is the pressure of water, and this is based on Pascal's Principle. So this big P is the pressure, This H is the height of your water column. G, this is little g, this guy that we've been talking about all the time. Remember, he's 9.8. You guys have really gotten a lot of mileage out of him because I made you memorize him a long time ago and you're still using him. And then this weird one, this is rho, I believe. It's a Greek letter, and this is the density of an object. So you can kind of figure out what the pressure is acting on something going really deep. So like if you have one of these submersibles, you'd want to know the pressure acting on this. If you go too deep and this submersible isn't rated for that pressure, this glass area, and actually the whole machine could actually start compressing, and then the glass will eventually break and these guys will die. So you want to be really careful with that.